So here in this question we have to use the concept of circumradius and inradius. So we know that circumradius is meeting point of all the perpendicular bisectors of a triangle, and circumradius is given by A into B into C divided by 4 times its area, 4 times the area of the triangle, whereas A, B and C are the length of the 3 sides. Similarly, in radius is given by area upon semi-perimeter, delta by S, and this ratio we have to find out for an equilateral triangle. So in an equilateral triangle we have all 3 sides equal, so A equals to B equals to C, so that makes it A cube divided by 4 times area will make this 4 into root 3 by 4 A square. If A is the side of the equilateral triangle, this is the area of the equilateral triangle. Similarly, in case of finding in radius, in the numerator we'll write the area of the triangle, that is root 3 by 4 A square divided by semi-perimeter. Perimeter is 3A, A plus A, and semi-perimeter therefore will be 3A upon 2. And from here we'll get the value of R as, let us cancel the common factors, A square, and we'll have A here, and this 4 will cancel out each other and we'll have A upon root 3. Similarly over here we'll cancel A and this will become 2 and we'll have A upon 2 root 3. So taking the ratio of R upon R, we have A upon root 3 divided by A upon 2 root 3. Again we see that A cancels out each other, and this root 3 also cancels out each other, and we have 2. That means circumradius is twice of inradius. After such a lengthy calculation, we have arrived at the value R upon R is 2. But now let us try and look at it in a different way. In an equilateral triangle, we know that all the 3 sides are equal and all the internal angles are also equal. Only in case of an equilateral triangle, all the points inside the triangle like circumradius, inradius, centroid, or any other point inside the triangle, even orthocenter, they all are at the same location. So if we draw perpendicular bisectors, all perpendicular bisectors will meet at a common point. The same common point is also the point where all the medians meet. The same common point is also the point where all the internal bisectors meet. So therefore this point is the centroid, is the incenter, as well as it is the circumcenter. So if it is the incenter, that means I can draw a circle by keeping this incenter as the center such that it touches all the 3 sides of the triangle simultaneously, and the radius is inradius. If this is the circumcenter, we can draw a circle which touches all the 3 vertices of this triangle, and this part will be the circumradius part. But at the same time, keep in mind that this is also the centroid and this length is also the median. We know that centroid divides median in the ratio 2:1. That means the upper part is 2 parts and the lower part is 1 part. But in case of equilateral triangle, the upper part is circumradius and the lower part is inradius, which is 2:1. So I took so much time in explaining because I wanted to clarify many other concepts related to that. But if you were attempting this question in a test, you should have immediately realized that circumradius and inradius are nothing but the lower and upper part of a median, and a centroid divides the median in the ratio 2:1. So circumradius would be the larger value, that is 2 parts, and inradius would be the smaller value, that is 1 part. So 2:1 immediately you would have got as the answer, which we have obtained from such lengthy calculation. But then this calculation also helps us in revising the formula for circumradius and in radius.